Today we're talking to Professor Erica Carlson, a theoretical physicist at Purdue University. And she studies electrons and how they flow through different materials. In particular, one of her areas of study is superconductivity, high temperature superconductors. How electrons can travel through a material and not get held up at all. So they can travel through without losing any energy at all.
My name is Erica Carlson. I'm a professor in the physics department at Purdue University, and I'm what you call a theoretical physicist. So there's two kinds of physicists in the world. Some of us do mathematical equations on paper. Those are the theorists, and we try to figure out the way the world is supposed to be. The other half are experimentalists, and they do experiments in a laboratory, and they measure things, and they figure out the way the world is actually happening. And then we compare our answers, and sometimes we agree and sometimes we don't. When we don't, that's the fun stuff. I work on what electrons do inside of materials. And that's a branch of what's called condensed matter physics. And you've probably heard about solids and liquids and gases and how those are different phases of matter. And it turns out that electrons inside of a material have their own phases that they have. So for example, you're familiar with metals. Metals, there's a metal inside here to carry current along, and so if I put a voltage on the wire, the electrons will start flowing, and that's a liquid-like phase of the electrons. Whereas if I tried that with, say, this plastic thing, and I tried to put a voltage across the plastic, the electrons wouldn't flow. They're stuck. They're much more solid-like in this material. There are other phases of electrons, like your refrigerator magnets are another phase of electrons. That's where the electrons are going in small current loops, nanoscale current loops, and then they make a little electromagnet, and if they all line up, they turn into a permanent magnet. That's your refrigerator magnet. It's a new phase of matter. I study these guys. This is a pellet of yttrium, barium, copper, oxygen. It's a high temperature superconductor. It doesn't look like a conductor, does it? That's part of the excitement of it, is that this is actually a ceramic material. It's ceramic just like your plate is ceramic. If you drop it, it'll crack. If you step on it, it'll crush. And if you feel of it, it doesn't feel like a metal, doesn't feel like a conductor. It doesn't feel cold like a conductor. It's not shiny like a metal. Nothing metallic about it. And in fact, when it's room temperature like this, it's not a conductor at all. But it turns out if you get it really cold as liquid nitrogen or colder than that, it turns into a perfect conductor, which is a superconductor. So let me show you how you can demonstrate that it's a superconductor. What I need to do is get it cold first. So let's do that. This is liquid nitrogen in here, and I'm just going to pour it over the superconductor. And we'll let that cool off a little bit. So now we've got the superconductor cooled off, as cold as liquid nitrogen, which is 77 Kelvin. That's really cold to you and me, so don't touch this with your bare hands. I have some nice tweezers to help me touch things. And what I'm going to do is float a magnet over the superconductor. But let me first show you that this really is a magnet. So I have here two magnets, and you can see that they attract each other. So these are magnets. This is a pellet of the high temperature superconductor at room temperature, and nothing particularly exciting happens between the two because this is too warm. It's not superconducting. This one inside the liquid nitrogen is cold enough to be a superconductor right now. So one of the ways that you can show that it's a superconductor is that superconductors hate magnetic fields. So this is a permanent magnet. It's got a magnetic field in it. And so the superconductor will cause that magnet to levitate. And if you can see, this really is levitating to the point where I can spin the magnet, for example, and you can see it's a frictionless thing. Okay, and I can take it away and put it back again, and you can see there's a few stable spots for that. There's a nice good spin. So one of the things that people are excited about with the high temperature superconductors is not just that they become perfect conductors. If you could replace everything in your house, by the way, with perfect conductors, you would save a lot on your energy bill because you currently pay for a lot more electricity than you get in your house. But one of the other properties of superconductors is that they float magnets like that. So you might imagine that if you could get a whole lot of these in a row, you could make a levitating train that was nice and frictionless. So you might be wondering what it is that I study about these materials. We are currently trying to figure out how the heck they work. because like we said, they're ceramics. They really have no business conducting at all. Yet when we get them cold enough, when we put liquid nitrogen on them, they become perfect conductors, which are called superconductors. And superconductors are very nice in a lot of ways, but one of the ways that they're nice is that you right now, for example, pay more money for the electricity that gets sent to your home than you pay for more power than ever actually makes it to your home, because a lot of the power gets radiated away as heat in the lines, because this, a metal, is not a perfect conductor. It's just a conductor. So it actually loses energy as it carries current. Whereas a superconductor doesn't do that. So that would go a long way towards solving the energy crisis. If we could figure out how these materials work, then we could figure out how to make them work at room temperature. And that's what I work on, is how in the world do these guys work? I got interested in physics when I was a kid. I was interested in a lot of science because I'm interested in how the world works, and I thought it was so fun to learn about how things around me work. And so that carried naturally over into physics. Physics is fun because we use logic to figure out how one idea is connected to another idea and so on. And using a very small set of things that we already know, we're able to use logic then to get to the next step and figure out the way that the world should work based on what we already know. And that's why I like physics. What I like best about being a theoretical physicist is that I get to think about really incredible deep problems. So for example, the first paper that I ever wrote was based in infinite dimensions. You and I live in 3 dimensions. I can move forward, backwards, side to side, up, down. That's 3 different directions. Yet, as a theoretical physicist, I can think about things not just in this universe, but what if the universe were a little bit different? What if we didn't have 3 dimensions? What if we had 4, 5, infinite dimensions? So I thought it was incredibly exciting that I get to do work on things that may or may not exist, including extra dimensions.
Are we on?
Yeah.
Okay. Oops.